One kid was like missing an eyebrow or something like that. You know, one kid had a scorch mark on his ear or something. It was like a little angry wasp, right? Because it had no guidance. It just was, you know, doing this random sort of dance, kind of like a garden hose. If you turn it on full thrust, right, and it's like going like this, yeah. Only that's bad with it when it's flame and you're standing there. Whoa, what was that, right? You know. Okay. So Estes rocket engines fly. They've got fins, and the fins provide guidance. Right, but a Saturn V rocket goes pretty slow for a long time, doesn't it? Or it seems to, right? It's a tall tower. It's 300 feet tall. It clears it in seconds, so it's not really going slow. It just looks slow. What keeps it from tipping over? Do you guys know?
Magic.
Magic, no.
The railings.
Not the railings on the side. It's not an. Yes.
It's too heavy to tip over?
Too heavy to tip over. No. Heavy things can tip over. Okay. Watch Apollo 13. Okay, there's a scene where the thing is going past the tower. You see it going shh, right, and as it lifts off, right? And as it goes by, you see all these little nozzles on the side of the rocket. I mean, this impressed me, right? And the nozzles are going, yeah, right? All up and down the rocket, there are little things called, I think they're like attitudinal adjustments. There's little thrusters. And if the rocket ever starts to tip one direction that it's not supposed to, okay, the computer knows it. There's gyroscopes and things aboard this thing. It's very clever, right? To be sure, without the guidance system, it's just going to fall like cut timber, right? But with the guidance system, as soon as it tips one way, a little thing goes, oh, better fire, puts it back, right? And in fact, it's exactly programmed. You should go to like the Saturn V, if you're really into this, go look up on Wikipedia Saturn V rocket, right? It actually was programmed to tip 1.5 degrees away from the tower until it cleared the tower. And then it's exact. At exactly this time, it would tip exactly this point. They programmed the wind into it, right? The wind that it would encounter. They programmed that into it and made adjustments for that. This rocket is pointed exactly where they want it to point because it's got computers. It's got all these little thrusters that can point it exactly in the direction it's going to go. Now, the original rockets that they made in Germany, if you look at those tests of those rockets, a lot of those just fell over and went boom. Right, because presumably they didn't have transistors and gyroscopes and, you know, all this clever stuff. So that's sort of interesting. And there's the big Saturn V rocket. This is a picture probably from the east or the west, and you can see that it actually has tipped away from the tower like that as it takes off. And the first stage and the second stage, we talked about that already. The LEM, the escape. Like this. And then this is the everybody wants to talk about ion propulsion systems, right? There are electric rockets. There are rockets that work on electricity. Electricity is free from the sun. So if you have a mission, a NASA mission that's going to stay in the solar system, you just have solar panels pointed toward the sun. These rockets have exhaust gas velocities typically 20 to 50 kilometers per second. That's pretty good, isn't it? The Saturn V's exhaust gas velocity was about 2.2 kilometers per second. Right? This is somewhat better than that, right? Okay. But the interesting thing about these things, and the way they work, is that you take an ion source. Typically, it's like xenon, some real heavy atom, right? This is a noble gas, so they've got a big tank of xenon. You ionize the xenon by taking electrons off it. You accelerate it toward this grid, right? And some of them pass through the grid and fly off into space at 20 kilometers per second or something like that. And then here's a problem. If you're always spewing positive ions into space, don't you become negatively charged? And your charge is going to build up and build up and build up. Eventually, aren't they going to come back to you? Doesn't that cancel out your thrust? Yeah, imagine I throw the ball that way and I go, right? But it's really on the end of a long rubber band. And it goes, and then it slows down, stops, comes back to me. Doesn't that cancel the thrust that I got from throwing it? Yeah. So what they have to do is they have to actually spray those ions. They have to spray negative ions into that stream as they're leaving, going, oh, take these electrons with you. Yeah? So all the electrons that they took off to make these things positive ions, they've got a red hot wire here that's just bubbling those electrons into it. So as they fly by, they pick up an electron and go, thank you. And off they go, right? Yeah? Yeah? That's kind of
UFO.
The Dawn, there's a Dawn. I don't know what the Dawn mission is, but it's I think it's in the solar system here. There's a picture of it, and this is just a diagram. This is called a gridded xenon ion drive. Sounds like Star Trek or something like that, but there it is, right? And then notice prominently, what's powering this rocket, this spacecraft? Yeah, it's electricity. This is an electric engine, right? You can also get electricity from nuclear, like a little nuclear reactor or something aboard that. If you read 2001 Space Odyssey, presumably those rockets are powered by a nuclear power plant, right? So ion drives, the concept's been around for a long time. These kinds of rocket engines have actually been around for a long time. There's nothing terribly new about this, except that we're pretty good at this now. And then the other sort of interesting thing is that this thing generates about 1/10 of a Newton of thrust. Isn't that interesting? But it does it for a long time, yeah? Is it important that you have a lot of thrust if you're out in outer space? Not so much. So it's sort of like an insistent force on the object acting over weeks and weeks and weeks is going to get it up to some really, really high speed, right? And then we don't need to calculate this, but I figured out that it has to burn, it's burning about, well, this is 10 to the minus 6th. So that's micrograms of fuel per second. That's not very much, is it? Yeah, that fuel is going to last a long, long time, right? And then the big question is what the delta V is. What's the biggest delta V you can give a rocket? And it's an interesting question, right? Because the more fuel you have, the harder the rocket is to accelerate, correct? The more mass it's got, the more fuel you've got, the more mass you have. So the harder it is to accelerate. So you can't just put arbitrary amounts of fuel on a rocket. You've got to actually have really, really high exhaust gas velocities. And you have to make the rocket so that very little of it is weight that can't be burned, right? Or can't be shot off into space. You want to make the overhead, right? So anyway, I don't know. I thought that's interesting. Is that interesting? I think it's interesting. Do you think it's interesting? Well, I think it's interesting.